prove that there is no continuous and differentiable function h of x which satisfies the following properties. What have we got here? Okay, h of x is defined over the negative numbers. H of x is always increasing. Okay, h at -3 is 5. And h at x is negative whenever x is between -2 and 0. Okay, so we want to prove there is no function that does this. Now, just before I get into it, I'm pretty sure the continuous and differentiable mean, we should probably approach this with something like the mean value theorem for proper rigorousness. But it's always a good idea to look at these properties and try and talk your way through it. Does it make sense to you? Now, a casual argument, and this needs to be clear, is not a proof. Okay? You do need to build things up with math results and logic and inequalities and all those sorts of things. You can't just say, well, I can't imagine. Every time I draw a picture, this happens. I can't imagine anywhere else or something like that. You've got to actually go through and use hardcore math results. Well, maybe not hardcore, but established math results. But let's first think about it. So let's just look and sort of imagine. Okay, we only need to look at the negative numbers, so we'll just look at this side of the x-axis. Now, we know we've got at -3, we have to be up here at 5. And so negative numbers increasing up at 5, none of that seems like it'd be a problem. I could definitely imagine a function like that. Okay, and then also h is negative whenever we're between -2 to 0. And I think that's where we're going to start to run into a problem, because negative means h of x is somewhere down here. Well, if it's always increasing, how did it go up and come down here? Now, it could kind of be like 1 over x, right? 1 over x goes down, and then suddenly it comes from the top. 1 over x is always decreasing. Well, this guy's always increasing. So couldn't it maybe go up through this point and then wrap around or something like that? Well, it could, but that would require maybe sort of a discontinuity. We know we're continuous. We know we're defined here. So that's sort of an issue. So it's not just, oh yeah, increasing messes with negative. It's that there's sort of no escape. The fact that you have to be defined at all these points, we know we're continuous, differentiable. Increasing, you can't go from 5 down to the negative numbers down here. So that makes sense to me, but how would I actually approach explaining that properly and rigorously with math? And as I said a moment ago, continuous and differentiable really suggests to me that maybe we want to go out of our way and use the mean value theorem. Okay, so mean value theorem, differentiable, we might start thinking, okay, increasing means h prime is never negative, right? That can't happen. And yet, we go from 5 down to a bunch of negativeness, so, some negative number down here. This line here has negative slope. Well, the way the mean value theorem works is between these 2 points, the function, however you draw it, will also have to have this negative slope. Its derivative will be negative, and so that would mean you can't be increasing. So that's kind of a plan of attack. Now, the way we're going to actually write this up properly is a proof by contradiction. We're going to assume that there is an h where all this works, and we're going to show that because of that, the mean value theorem will force this function to do something that is garbage, is nonsense, is logically inconsistent. So here's what we'll do. So towards a proof by, I'm going to write it up nice and neat. Towards a proof by contradiction, assume there is such a function h of x that is continuous, differentiable, has all the parts, like defined over the negative numbers, everything like that. Okay? So, where can we go from here? Well, to use the mean value theorem, we have to, the mean value theorem, we're going to have to show it's continuous and differentiable, continuous over a closed interval, differentiable over an open interval. And so the next thing I would think is, well, what sort of interval? And there's not an obvious one in the question. Remember, the mean value theorem uses sort of an h at b minus h at a over b minus a. Now, we do have h at -3 is 5. So that'd be 1 point, but I don't have another point. They don't give me anything, any other points here. They do give me sort of this vague statement that somewhere over here there's some value, and you know it's below the x-axis. You know it's negative. But they don't give me anything precise, and that's okay if we're willing to work just with properties. If you're in the mindset of you have to always have exact numbers and formulas and everything like that, you're limiting yourself. Okay? So we might say something like, okay, well, this is property 3. So it's property 3. Okay? And then let's pick a number between -2 and 0. It doesn't matter what that number is. I'm going to choose -1 just for my own sanity, just because it's a nice, easy number to work with. But what I'm about to do, you can do with -1/2, -1/3, -3/4, -pi/2. You can do it with lots of numbers, okay? I don't want anyone looking at what I'm about to do and saying, well, how did he know it had to be -1? Okay? But here's what I'm just picking some number because I need to get another point. How do I know I need another point? I'm going to use the mean value theorem, and that requires, we've just sort of got our A, but we need our B. So let's let h at -1 be equal to, it'll be some negative number, that's why I'm calling it n. Okay? So we know it, we could say something like we know it exists by 1. Actually, let's even say that. So we'll say it exists by property 1. And by the fourth property, we know, let's say, since -1 is in between -2 and 0, that's why I chose -1, because it's in there, we can see n has to be negative. And that's all we know about it. We have no idea what this number is. It could be negative a billion. It could be negative a billionth. But we know it's negative. Okay? So now, we might say, well, since h is continuous and differentiable everywhere, well, everywhere that it's defined is sort of the way to read it, because all we know right now is that it is defined from -infinity to 0. It might be defined for other values, but they haven't told us that. That's not something we can assume. But because of that, we can say h is continuous on our closed interval from -3 to -1. And again, -3 is from the problem. -1 was arbitrary. It could be -0.5, but I think the b minus a will be kind of messy. And we would say, all right, and it's differentiable on this open interval. I mean, it's differentiable everywhere it's defined, but we specifically call it the closed interval and open interval because I'm going to use the mean value theorem, and that's what we're going to move on to next. So we could say, the mean value theorem applies. Right? Especially if it's a named result, it's always a good idea to explain. How do you know you're going to be doing this? Well, okay, because it's continuous here, differentiable. That's what goes into the mean value theorem. So we'd say, all right, we conclude there is some c in between -3 and our chosen -1, so that h prime at c is h at -1 minus h at -3 over -1 minus -3. Now, I don't know what n is, but I do know it's negative. H at -3 is 5, and then -1 minus -3 is 2. So here's what I would say next. Look, since n is negative, n minus 5 is negative, and since 2 is positive, dividing by 2 doesn't change the inequality sign. So, I mean, 0 over 2, but 0. So this value is negative. So h prime at c is negative, which would tell us, so I might say which would imply h is decreasing. Let's say h of x at this mystery c. I don't know where c is. I know it's somewhere between -3 and -1, but I know we are decreasing at that point, but which we might say contradicts property number 2. So all we did was assume there is an h that has these 4 properties, and we've shown that the mean value theorem forces something to happen which we know can't happen. We have something false. Okay? So we have what we call a contradiction. Now, how does that work? Okay, you get something false. Well, that just means that what you assumed couldn't possibly be true because it led to something false. True things, if you follow them through logically, only lead to true things. So how can we get something false? Well, it means we must have started with something false. And so by contradiction, we can conclude there must be no such h. And there we go. We're all done.